Hello, my name is Stéphane Farou. I am a database performance consultant. For me, there is a clear link between performances and the understanding of what happens inside the database. I've had the opportunity to witness that for many developers, the persistence layer is kind of cloudy. I'd like to take you behind the scene and explain without getting too much into details how everything works. I'll start by explaining what happens when you start the database, something which is most often automatically performed by scripts when a machine boots. I'll talk more precisely about the Unix implementation of Oracle, but it's not massively different under Windows. An administrator who wants to manually start a database, called a server by some other products, must have at least two important variables set in his environment or in the registry. A variable that says where the distribution of Oracle has been installed, called Oracle Home, and a variable that identifies the database, called Oracle SID. You can have on the same machine several different databases running that may be running under different versions of Oracle. The administrator will run the SQL Plus program and connect. Actually, the connection is dummy at this stage. It's just to check that the program is invoked from a Unix or Windows account with the right privileges. You can then run the magical startup command. The program starts by reading a file called spfile oraclesid.ora that contains the parameters for the database identified by Oracle SID. It's a binary file, and you may hear about the init.ora file, that is a text file that historically predates the binary file. Database parameters will give the size of a shared memory area that is allocated at this stage and which is called the System Global Area, or SGA. This is where Oracle works. A number of utility processes will also be started. The number increases with each version of Oracle. Some of them are mandatory, others are optional. Under Windows, there aren't processes, but threads. All of the processes are running the same Oracle program and have the SGA in their address space. When memory is allocated and processes started, SQL Plus displays the total SGA size, as well as the size of four subparts: the fixed part, the variable part, the database buffers, and the redo buffers. At this point, Oracle is going to open and read a file that is so critical that it's always duplicated, the control file, found at a location that is specified in the parameter file. This is where Oracle finds the names of all the data files, temporary files, and log files that together make up the database. The control file will also allow to check global consistency, whether something needs to be restored, and whether the database was properly shut down or if some unfinished transactions will have to be rolled back. Without a control file, your database is dead. After passing this stage, SQL Plus will display that the database is mounted, which mostly means that all files are identified. The only step that remains is the opening of the various files for read-write operations. When files are opened, then the database is open and users who aren't database administrators can connect. That is, they can connect if they are logged onto the machine that hosts the database. If you want to enable users or an application server to connect from another machine, which is the most common case, you have to launch with the lsnr-ctl start command another program called tnslsnr, which is the listener that waits for incoming connections. After displaying a lot of intimate details about its configuration, found in the listener.ora file, the program runs in the background and everything is in place. Let's now contemplate a client program that runs on another machine. If it wants to access the database, it needs to provide, first of all, three pieces of information: the name of the host on which Oracle runs, the port on which TNS-LSNR is listening, and the service, that is in practice the identifier of the database you want to connect to. There are several ways to provide these pieces of information. You can directly provide everything in the function that performs the connection request. This is, for instance, what you do with JDBC and a pure Java driver. If your client is using the Oracle client libraries, you can also provide an alias, and your client will transparently fetch the associated information from a file called tnsnames.ora. These two methods are by far the most common ones. But there are other possibilities, such as using an LDAP directory or system utilities such as the Network Information Services as a substitute to the tnsnames.ora file. Obviously, Oracle will not give you uncontrolled access to the data. You must sign on so that you are identified and the database clearly knows what you are allowed to do. Usually, you will provide a username and a password. Authentication through an LDAP directory is also sometimes possible. In practice, your client issues a connection request that is handled by the listener. The listener will either spawn a subprocess that will run the Oracle code and become the client's dedicated server, or it will redirect the connection to an already existing shared server, which is a much less common configuration. The server process is, so to speak, the client's proxy on the Oracle side. It can access the SGA that is shared between all processes. It will also locate a private memory area called PGA, where it stores what is private to the process and to the session. But let's take a closer look to the various parts in the SGA. There isn't much to say about the fixed system area, but the variable area contains the shared pool, which holds compiled versions of queries, as well as various buffer pools that will contain, for instance, data dictionary information. The data buffer contains data from the tables, but also index structures and various work areas. Everything is split in pages or blocks. The block is the Oracle Basic Storage Unit, and a typical size for a block is 8K. Whenever you query or change the content of a table, you operate in memory on blocks that are in this cache. Finally, a fourth area is used to store information before it is written to log files to ensure transactional consistency, even in the occurrence of a crash. The parts that really matter to understand how Oracle works are the shared pool, the data buffer, and the log buffer. This is where the dedicated server process will operate, as well as the main utility processes started with the database. Let's see what happens when the client issues an SQL query. The query arrives as text to the server process that will start by computing a hash value that is used as a checksum. Then, the server will check whether this query has already been recently executed and will inspect the shared pool. If the query is found, the analysis stops here. This phase is called soft parsing, and the server process can execute the query. If a prior query with exactly the same text cannot be found, then we have hard parsing that is CPU intensive and locks some shared resources. SQL syntax must be analyzed, the objects that are referred to in the query must be identified, and the best execution plan must be determined among sometimes a very large number of possible execution plans. It may cause recursive queries on the data dictionary and input-output operations. This is why you shouldn't concatenate to the text of a query identifiers that change with every call, but you should pass them as parameters, as if the query were a function. Once the query is analyzed and compiled, it is going to be loaded into the shared pool and executed. It will then reference pieces of data that may or may not be in the data buffer. If data blocks aren't in memory, the server process fetches them from the data files and loads them. Blocks that have been modified are written asynchronously to the data file by one or several database writer processes. When you update data, mechanisms for analyzing the statement and uploading data blocks in memory are the same ones. But before modifying data, initial values are copied to a work area called undo segment. Another process that wants to read data being modified isn't blocked, but reads data from the undo segment instead of reading from the table block. Initial and new value are also copied to the redo buffer. If the redo buffer fills up, the utility process LGWR or log writer dumps its content to a log file. When you commit the transaction, Oracle records that the initial value is no longer required for rolling back the change. It records that the change is validated, and the LGWR process writes the transaction to the log file. This time, the operation is synchronous, and the server process waits for the go-ahead before the call returns to the client. That means that if you commit every single update in a loop, you will waste a lot of time just waiting for acknowledgement. This is a very quick introduction, but I hope it will allow you to understand better what happens. Thank you for your attention.